pardon me if I make no sense today.
Just like Mr. Chara.
Yeah. So, yeah, as Sandy pointed out, yes, I am going to Greece this summer for a research project, and what I'd like to do today is give you a little bit of insight on what things we are doing research on during those research visits, research projects. This topic that I'll be presenting is work that I did for my PhD along with my advisor, Vanier College, who is in Carleton University in Ottawa. He's actually not the reason I'm going to Greece, even though he is Greek. I'm actually going to visit a friend over in Greece. His name is Matthew, who is working on similar stuff. So the title of my topic is Broadcasting with Swamped Sensors. So we will be talking about transmitting messages in wireless networks. And these wireless networks are networks of what we call sensors. Sensor networks are, it's a very, very lively topic in research today. The goal is to produce networks of small machines that are able to sense things that are going on in the environment. For instance, maybe you want to sense temperature differences in the sea so that we can map out how the currents are going or whatnot, or maybe try to find out if there's some dangerous gases in a building, or maybe do some site surveillance in a secure location. So these sensors are very useful, and they're very heavily studied nowadays, and it's been that way for I guess maybe 2 or 3 years, or maybe 5 to 10 years. And the problem of broadcasting is to send a message. So we're going to be defining this swamping, which is a problem which occurs with all transmitters that are pretty cheap, because we want to have a multiplicity of these small transmitters in the field. So we can't pay a whole lot of money for each one of these transmitters. They have to be very cheap. And the swamping, this swamping effect occurs when we have those cheap transmitters. Okay, so I'll discuss where this comes from and how this differs from our ideal thinking about message transmission in the network. In radio communication, normally what we think is that in the ideal sense, if I have a device right here which is transmitting, it should be transmitting up to a certain distance, and past this distance, then the message does not reach that distance. So it goes up to a distance R, for instance, maybe 10 kilometers. And at 11 kilometers, the message does not transmit anymore. But the fact is that if I have 2 transmitters in the same vicinity that are transmitting on the same channel, then the message will be blocked, because it's just like 2 people talking over one another. You have 2 people talking over one another in an office, and nobody hears what anyone is saying. That's what we call a message collision. So, in reality, what happens in radio communications is that we have to be listening for a message, and we have to have only one person who is talking at a time. And we hope that if the person is close enough to us, he will be able to understand the message that we are sending. However, that's not the case. So reality is even more complex than this. I have here, I'm showing you a picture of actually a commercial product that is being deployed in old folks' homes to monitor if there is movement in the apartments, to know if maybe someone who is losing their autonomy has fallen on the ground and is not moving for a few hours, so that we can maybe alarm the security guards. A friend of mine is the director of research for this company. It's called Combat Networks. They're called Combat Networks, but we're still working on old folks' homes. Yes. I guess the Combat Networks came from getting military grants. Anyways, these sensor nodes, they suffer from this type of problem, that if they are too close one to another, like this distance, for instance, they are not able to talk with one another. They cannot communicate with one another. It's just like if I'm standing right next to you and I start screaming. You can't hear a thing that I'm saying because it's just too loud. So this is the problem that we call swamping. And this happens for all cheap transmitters. Okay. I'm not saying these are cheap. I know it's cheap. But this happens to all cheap transmitters. So the question is basically going to be how we can manage to still do some communication when we have this problem inside a very large network of these sensors that is spread in an environment so that we can monitor some event. So just to formalize a little bit the model, what we want to model here is that we have a node here. A node is going to be a transmitter, which is able to communicate with all nodes that are in the white portion here. Okay? So all these green nodes that are in the white portion can actually receive the messages that are sent by this red node. However, all those nodes in the red portion, they cannot receive the messages because it's just too loud in this region. So instead of communicating in a nice large disk area, the reality is that transmitters, cheap radio transmitters, can only transmit in this donut area. So we want to transmit in donuts, and we want to do it efficiently. And there's a lot of problems that comes with that. Lots and lots of problems that come with that. One of the problems is that in very large networks, there might be configurations of nodes, the way they are placed all over the network, that lead to particular problems. For instance, I may have here a smallish region that is inside which all of these nodes cannot talk to one another. And all of these nodes, if they wish to transmit the message to another group of nodes here to the right, they each need to transmit a message. Because all of these nodes only can talk with those nodes that are connecting them with this line. And they also need to transmit the message to all these nodes inside a cloud. We don't know where these nodes are. So our goal here is to actually find a scheme to transmit this information in a collision avoidance way so that all nodes in the end get to receive the message. And we wish to do this as fast as possible. Because it's very easy to say, well, okay, this node transmits and that node transmits, and it will take a very large amount of time. But our goal is to do it as fast as possible. So we want to have very efficient networks. One of the problems that comes with that, this is not the only problem with the swamping issue, is that, for instance, this node right here, which might be very close in the geometric sense to this node right there, may be very far in the network sense. So we would have to transmit a message through many intermediate nodes in order to be able to reach finally this node, which is very close, because we are transmitting in these donuts. So this node here would be in the red portion, where we cannot transmit, and this node is in the correct portion, the blue portion. There's a link, and then the message can be transmitted. So the distance between two nodes that should be very close in the network is, in fact, very large in the network. We say that this distance can be up to what we call the diameter d. This is the longest distance in the network, the diameter. All right. And what we wish to accomplish is broadcasting. Broadcasting is when we want to have a message sent to all nodes of the network. For instance, I try to broadcast a message in the entire school. It originates from one computer in the school, and I succeed in broadcasting if all the computers inside the school have received the message. The problem, how fast we can transmit, even with this problem of the swamping. Now, we are only going to restrict ourselves to networks that are connected, and we're going to implicitly think that there is a minimal distance between nodes, because nodes are physical objects, so they have a certain size. And it's very important that we fix that there is a minimum size between any two nodes, because then the antennas will not be able to be in the same location, in the same point. Without this minimum distance, it would be impossible to solve the problem. So we have to think about this. Okay, so we are doing here a very drastic approximation of reality and bringing it to a approximate mathematical model so that we can actually translate this into a real solution, a real algorithmic solution. Okay, so I'm not going to talk about all the processing that went on in my brain during this whole mathematical model, between the mathematical model and actual solution, but I am going to discuss the solution that we have found, which we think is pretty good, and how it differentiates from other solutions with weaker problems when we have correct transmission, not this swamping model. So we have an algorithm that does the broadcasting in 2 steps. The first step is that of network discovery, and the second step is collision avoidance. Now, why network discovery? What I did not mention is that we are sending these nodes on a field somewhere, and these nodes have no idea where the other nodes are. They have not been pre-programmed with these locations ahead of time, but they do know where they are, because it's very cheap to place GPS receivers inside the sensor node. It's about $5. But it's impossible to pre-program the locations of other nodes inside these transmitters. So we need to do this network discovery. And then there is the collision avoidance. So the way that we do this, the technique that we use, is we take the region where the nodes are spread out, and we cut it into small squares. And this technique here, is actually very standard when it comes to communication problems, where we don't know where the network nodes are. So you may want to remember this type of technique. And there's 3 levels of partitioning going on here, and each level has a reason. So I'm going to explain quickly, briefly, the reason for each level of partitioning. We partition the entire plane into what we call regions that are distance 3 by 3. 3 by 3 because the transmission range would be normalized to 1. And we wish to avoid any collision between transmissions. So we just basically picked a number that is larger than 2 plus a little bit, 2 plus this small number right here. So we'll just pick 3 just to keep it simple. And then we wish to partition further this grid here into smaller boxes of size, basically the squares that have a diagonal size of L. And this distance L here is picked so that we can ensure that a small selection of nodes inside this square, if they transmit, then all of the neighbors of nodes inside the square receive the message. This is extremely important to ensure correct transmission of data. And then the 3rd level of partitioning is done to ensure that no 2 nodes transmit at the same time because of the physical constraints of these nodes. Because they have a certain size, by making those squares having a size of alpha, we know that there's not going to be 2 of them inside one of these squares because they have a minimal distance between one and another.